In this video, we will explore how to create submodels that take into account different boundary conditions for the same structure, avoiding the need to duplicate SAP 2000 model files. We will focus on the steel structure model that has already been designed for a set of load combinations. On the screen, we see a deformed view of this structure for one of those load combinations. In this model, soil structure interaction was not considered, so the supports were simulated as fully fixed. Now, let's look at a brief summary of the design checks according to Eurocode 3, presented as demand capacity ratios. We see that the central column has the highest ratio, at 0.902. Next, we switch to a copy of this steel structure model, where we do account for soil structure interaction. Once again, we observe a deformed view of the structure under the same load combination as in the previous model. This time, the central column has a lower demand capacity ratio, but the left column now shows a higher ratio of 0.925. The question becomes, how do we handle design when we want to consider both scenarios, one with fully fixed supports and one including soil structure interaction? If we only had a few members to worry about, it might be easy to track which model governs each one. But in larger models, identifying the controlling scenario for each member is not so straightforward. Moreover, any future modifications would require updating multiple models. We also wouldn't be able to produce a single comprehensive report covering all boundary conditions. This extra work increases the risk of mistakes, both when editing the various files and when verifying the structure. So why not incorporate both situations into one SAP 2000 file? That's exactly what we'll do next. Let's unlock this second model and edit it so that we can handle both situations. Our plan is to create two submodels within the same file. First, we need to define the support properties in a way that can be switched on or off. We'll insert rigid link elements at the base of the columns to represent fully fixed supports when needed. Since we can't directly remove or modify fixed restraints to achieve a second submodel, we'll define these rigid links with high stiffness. Specifically, we might use 1 × 10 to the 11th kN per meter for translational degrees of freedom, and 1 × 10 to the 11th kN meter per radian for rotational degrees of freedom. That value is high enough to simulate a fixed support but not so large that it causes numerical issues. We then turn off extruded view so we can easily draw these link elements at the base of our 9 columns. Next, we'll create 3 groups, one for the mat foundation, one for the steel framing, and one for the link elements that will provide fixed support in the alternative submodel. Now we assign each object to its respective group, the mat foundation elements to the first group, all steel members to the second, and all link elements to the third. We're ready to produce 2 submodels. First, we define a load case using the stage construction option for the model with soil structure interaction. This submodel will have both the steel framing and the mat foundation. We use a single-stage approach here, which is compatible with SAP 2000 licenses ranging from Plus to Ultimate. In this case, we add the steel structure and the mat foundation. Next, we can create a copy of this load case to build the submodel that is fully fixed supports. For that submodel, we only need to include supports instead of the mat foundation. Lastly, we have to duplicate the load cases so we can generate results for both submodels. For now, we won't worry about which version of the model each load case is linked to. We can handle that more efficiently through interactive database editing. Also, if we have a response spectrum analysis, we might need to switch the modal case for the fixed support submodel. We'll do that in the database tables as well. So, let's use the interactive database editing to edit the load cases. Now we can finally edit which models are used for each analysis. For the initial load cases, we choose the MAT Foundation model. And for the copied load cases, we select the fixed supports model. We also change the modal analysis for the copied response spectrum case. We apply these changes. Let's now check the dead load case to verify that the update has taken effect. We see that it's using the MAT Foundation model. Now let's look at the copy of this load case. This load case is using the fixed supports model. Let's now check the load case tree. We see that the MAT Foundation submodel is being used for all of the original load cases, including the response spectrum analysis that relies on the modes for this scenario. We also see that the fixed support submodel is assigned to the other load cases. Next, let's graphically examine the submodels in use. For example, the dead load case applies the model with the MAT Foundation, no fixed supports. Meanwhile, the copy of the dead load case uses the fully fixed base model, no MAT Foundation. We notice there are 14 load combinations in total. We need to replicate them in order to perform design checks on both submodels. This can be done very quickly through Excel. All we have to do is duplicate all the combinations. Then append the load case suffixes. And finally add suffixes to the load combinations themselves. We can bring those changes back into SAP 2000 and apply them to the model. Let's look at the ULS1 combination in its original form. And here is its copy, which is set to pull results from the fixed support submodel as intended. We're now ready to run the analysis. The results are now available. Before moving on to the design checks, let's check the deformed shape for the dead load case. And here's the deformed shape for the fully fixed model without the MAT Foundation. Finally, we can define the design load combinations. We'll include them all so that the models with both boundary conditions are checked together. Now let's review the final results. We confirm that for the central column, the fixed supports model is the governing one, with a ratio of 0.902. We also confirm that the left column is governed by the mat foundation model, at 0.925. For instance, this corner column shows a ratio of 0.674 from mat foundation, while the other facade column comes out to 0.701 from fixed supports. By adopting this strategy, we keep all submodels inside one SAP2000 file, generating a single project where we can handle multiple boundary configurations, soil structure interaction alongside fully fixed conditions, without duplicating effort. This integrated approach streamlines our design checks, reporting, and future revisions, significantly reducing the chance of errors. In summary, we used rigid link elements to represent fixed behavior, created separate submodels for each boundary scenario, duplicated our load cases and combinations, and made sure the design process captures both conditions simultaneously. As a result, we can confirm which scenario governs each steel member and compile a single comprehensive output, all while minimizing repetitive editing and potential oversights. That was all for this lesson. Check the rest of our tutorials to master SAP 2000 and other engineering software.